Hello everyone, my name is Abhiraj Chouhan and I am a student of MTech-IT 4th semester. Today I am solving end semester question paper of numerical analysis and design for my assignment. So let's start with question number 1. Question number 1 asks us to find the root of nonlinear equation fx is equals to x square minus x minus 1 is equals to 0 using numerical methods like bisection method. Performing several tasks, let's start go through each part systematically. Algorithm and flowchart for bisection method. The bisection method finds a root in an interval a b where fa and fb have opposite signs, ensuring root exists. The algorithm starts by checking if fa and fb is smaller than 0. If true, we compute the midpoint c is equals to a plus b by 2 and evaluate fc. If fc is below a tolerance or interval, a and b is sufficiently small, c is the root. Otherwise, we check the sign of fc, and if fa multiplied by fc is smaller than 0, the root is in a and c. So if so, set b is equals to c. Otherwise, in c and b. So set otherwise it is in c and b. So set a is equals to c. We repeat until convergence. I have included the algorithm in the presentation, as you can see. Let's move to part B, iterative calculation. For fx is equals to x square minus x minus 1, let's choose b is equals to 1, 2, and since f1 is equals to f1 minus 1 is equals to minus 1, and f2 is equals to 4 minus 2 minus 1 is equals to 1. So f1 by f2 is smaller than 0. First iteration is equals to c. That would be equal to 0 minus 0.25, since f1 and f1 into f2 is smaller than 0. The root is in 1.5 comma 2. Second iteration c is equals to C would equals to 3.0625 minus 1.75 minus 1 is equal to 0.315. Now f1.5 into f1.75 is smaller than 0, so the root is in 1.5 comma 1.75. Continuing this, after few iterations, we convert to approximately 1.618, which is close to the golden ratio, a known root for the equation. Moving to the third part, part C, interpretation. Geometrically, the bisection method halves the interval at each step, bracketing the root where fx crosses the x-axis. For fx is equals to x square minus x minus 1, the parabola opens upward, crossing the x-axis at the root. Now each iteration narrows the interval, visually converging to the root. Coming to the part D, error estimation and convergence. At each step, the absolute error is half the interval length. After the k iteration for 1, 2, after 5 iteration, the interval is 1 by 2 in power to the power to 5 is equals to 0.03125. So the error is about 0.0156. Relative error depends on the root's value, roughly 0.0156 divided by 0.618 is approximation to 0.096. The method converges linearly with order 1 as the error halves in each step. I have tabulated these results in my slide for clarity. Now moving to the our next question. Question 2 involves using Lagrange or Newton interpolation to estimate F9 given and in the given data points. Let's use Lagrange interpolation. Let's use Lagrange interpolation and address for each part. Coming to our part A, assumption and polynomial degree. Lagrange interpolation constructs a polynomial that passes through all the given points. With 5 points, the polynomial is of degree at most 4. We assume the underlying function is smooth enough to approximated by polynomial of this degree, and we will stop when the polynomial is fully determined by the points. Coming to the part B, computation of F9 or using 3 or 4 points. The Lagrange formula in the Lagrange formula where Lix is equals to for x is equals to 9, we compute each Li and L0 as shown in slides. Thus, F9 is equals to 150 into minus 2 by 2 third plus 392 into 4 by 3 plus 1452 by 1 third plus 23660 plus 52020 is equals to minus 61.33. As you can see in the slides, the all the values written. Coming to the part C, the program or algorithm, the question asks us for to write. The algorithm for Lagrange interpolation takes points xi and xy and target x computes each li and sums yi lix. I provided the pseudocode in my slides as you can see. Coming to the part D, comparison on the graph. The degree the degree 4 polynomial passes through all points, but at x is equals to 9, f9 is equals to minus 61.33 lies below the trend of the data, suggesting the polynomials may not capture the function's behavior between points due to high dense oscillations. Coming to the last part, part E, error estimation. The error in Lagrange interpolation is fx minus px is equals to fn plus 1 and n plus 1 without knowing f. We can't compute this exactly, but the negative value at x is equals to 9 indicates potentials phenomenon where high degree polynomials oscillate. The slide includes all the. Let's come to question number 3. Question number 3 asks us to estimate the first and second derivative at x is equals to none using numerical differentiation with the same data point addressing three parts. Let's solve it. Part A is algorithm and flowchart. We will use central differences for better accuracy for first derivative and second. Since x is equals to 9 is a data point, we first interpolate to find f9 from question f9 f9 and then choose points around x is equals to 9 like x is equals to 7x and x is equals to 11. So h is equals to 2. The flowchart involves interpolating f at nearby points, applying the difference formulas and computing the derivatives. Part B, steps by steps numerical differentiation. We will use neutral divided difference formula and solve this by in the different steps. First steps divided differences and second is divided difference. Now coming to the last step is differentiate. We will differentiate the function at x is equals to 9. And coming to the part C, final results. Using f is equals to 7 is equals to 392, f9 is equals to minus 61.33, f11 is equals to 1452, f9 is approximately is equals to 265 for the second derivative. If f9 is approximated to 491.67. These are rough estimate due to large h and interpolation error. Part B, error estimation. The error in the central differences is f is oh to the power 2, so h is equals to 2. It is significant for f. The error is also oh to the power 2 without a true function. We can't quantify the error exactly, but the large h suggests the values are approximate. My slides detail the calculation. Coming to question number 4. Question number 4 has two parts about numerical integration. Part A for formula for numerical quadrature and Simpson's Weddle rule. Numerical quadrature approximate integration of a to the power b fx dx using weighted sum Simpson's one-third rule for 3 points is h by 3 fx0 plus 4 fx1 plus fx2. Weddell's rule for 7 points is derived by applying Simpson's rule over the subintervals and adjusting weights. I have derived this in my slide using Newton-Cotes approach. As you can see, we have derived the Simpson's rule using the Newton-Cotes quadrature formula with three equally spaced points over interval A and B, A and B. As you can see, we have done it from general quadrature formula. Simpson's one-third rule is. Now coming to the second part, algorithm for Weddell's rule. The algorithm takes 7 points xi, fxi, computes h is equals to xx, x0 divided by 6 and applies the formula above. If it checks the number of every point is exactly same and assumes equal spacing. As you can see, we have written the algorithm for Weddell's rule here. Weddell's rule is a Newton Cotes rule of degree 6 for 7 points, 6 interval with weights. Weedle's rule algorithm is step one. It takes input fx, lower limit and upper limit, and then calculate h is equals to h minus a upon 6, and then compute x0, x1, continuing to x6 and corresponding fx, and then apply the values to this formula, and it gives output. Now coming to our question number fifth. Question number fifth asks us to write an algorithm for 5-point Gaussian quadrature to compute integration of 0 1 integration of 1 0 dx upon 1 plus x square and then evaluate the pi. Let's solve it. The 5-point Gaussian quadrature formula for the given derivative is where xi are roots of the fifth polynomial and wi are weights. For n is equals to 5, the nodes are approximately xi is equals to 0 plus minus 0.538469 commas plus minus 0.90618 and weights wi is equals to 128 by 225 comma 322 plus 13 root 70 by 900. We transform the integral to 1 minus 1 to the power 1 by letting t is equals to 2x minus 1, so x is equals to t plus 1 divided by 2, tx is equals to dt by 2. The integral becomes 1 by 2 dt. Applying the formula we get 1 by 2 1 by 2 wi 1 by 1 plus x plus I plus 1, which gives us an approximation to 0.758, which is pi by 4. Since integral is equals to arctan 1 minus arctan 0 is equals to pi by 4, thus pi is equals pi is approximated to 4 into 0.7854 is equals to 3.1416, very close to the pi. The algorithm and calculation are in the slide, as you can see. Now coming to our next question, question number 6. Question number 6 asks us to solve the given system of linear equation using any direct methods and apply pivoting. Let's let's use Gaussian elimination with partial pivoting. The augmented matrix is, as you can see here, we will pivot on column 1. The largest element is 3 in row 2, so swap rows 1 and 2, eliminate below the pivot. Row 2 becomes 1 1 2 3 1 and 3, and row 3 becomes 0 5 3 3 4 3 6 1 6 3. Pivot on the column 2. The largest element is 5 by 3 in row 3. Eliminate. Row 3 becomes 0 4 0 1 4 5 1 6 5. Row 1 updates accordingly. Back substitution gives x is equals to 1, y is equals to 2, z is equals to 3. And after all the solution, we get the updated matrix 6 0 0 18 minus 5 3 11 minus 7 by 3 minus 8 by 3 7 minus 5 by 3, minus 4 by 3, and then applying partial pivoting on column 2. And then after the back substitution, our final answer is x is equals to 1 by 19, y is equals to 4 by 19, z is equals to 5 by 19. To summarize this, we have explored a wide range of numerical methods today, finding root with bisection method, interpolation with Lagrange, numerical differentiation, integration with Weddell's rule, Gaussian quadrature for pi, solving linear systems with pivoting. These techniques are essential for tackling real-world computational problems. I hope my solution provided valuable insights, and all the calculation and algorithms are in my slides for your reference. Thank you for listening. Thank you for watching this video.